Having developed methods of projecting the spherical Earth onto the flat sheet of paper, there are many different permutations of the way we wrap the paper, and any subsequent mathematical adjustments we may wish to make to the result. These basic differences can result in literally hundreds of different types of projection, and each of these will have different properties. Some projections will be better for some applications, such as general geography, agriculture or land management, and other projections will be more suited to piloting and navigation. We need to decide what properties we need in a chart which is to be used for flying. Firstly, let's consider what we'd like from an ideal chart, which correctly represented the Earth's shape in every way. If such a projection existed, it could be used for any application. The first characteristic is that angles on the Earth's surface should be represented by the same angles on the chart. It is important to a pilot that if we measure a track angle off the map, it should be the actual Earth track between the same points. Ideally, scale should be constant all over the chart. However, as we shall see, it is not possible to have it constant everywhere. In this case, it is desirable to at least have it correct at one known point. Shapes on the chart should be the same as shapes on the Earth. Equal areas on the Earth should be shown as equal areas on the chart. So this is our list for an ideal projection for any application. But now let's consider how many of them are important for navigation. The first one, that angles on the Earth's surface should be represented by the same angles on the chart, is utterly essential. If we can't measure a track angle and know that it will take us along the desired path over the Earth, the chart is useless to us. This characteristic is known as orthomorphism, or conformality. These are two terms which are equally used, and they mean exactly the same thing. Orthomorphism is essential for plotting as well as route selection. We must, if we plot a bearing from a navigational beacon, be confident that it actually represents where we are on the Earth. So any chart used for flying must be orthomorphic. The next one on our list is that scale should be constant all over the chart. But as we discovered when considering basic projection theory, this is not possible. All we can do is choose a projection which minimizes scale distortion if it is important to us. However, it is essential that the chart does have a correct scale at some point, and we know the rate at which it changes. The next one is that, ideally, shapes on the chart should be the same as shapes on the Earth. But practically, it makes less difference than might be thought. As long as the shapes are recognizable, and the latitudes and longitudes are accurate, our brains are perfectly capable of dealing with shape changes. These two maps both represent the North American continent on different projections. Their shapes are similar, but not identical. However, we have no trouble in recognizing that they both show the same land shape. And finally, on an ideal chart, equal areas on the Earth should be shown as equal areas on the chart. This may be important in some applications, for instance, comparing farming productivity. But does it matter to a pilot? Pilots don't make comparisons of area when flying. So, the only properties in this list which are essential for navigation are orthomorphism, and that scale must be correct at some point on the chart. To have scale completely constant is not achievable. However, it is desirable to choose a projection which minimizes scale change. Within reasonable limits, shapes don't matter much, and area is not important to a pilot. What about navigation requirements? Again, an ideal chart would have the following characteristics. Rhumb lines should be straight lines. Great circles should be straight lines. Additionally, latitudes and longitudes should be easy to plot. Adjacent sheets should fit correctly, and coverage should be worldwide. Two of these properties can never be obtained, except on a globe. Scale can never be constant and correct. We can modify charts mathematically to give nearly constant scale in small areas, but not over large areas. The shapes of large areas cannot be represented perfectly. However, it is possible to represent the shapes of small areas reasonably accurately. All of the other properties can be obtained on charts, but not all on the same chart. Different projections capture different properties. Most of the projections in an atlas are useless for navigation, because they are not orthomorphic. Therefore, from the vast range of projections available, we have to select only those which are. The word orthomorphism comes from Greek, and the original Greek words literally mean same shape. However, for us, this is a misleading translation. As we have said, shape is not all that important. In mapping, orthomorphism means that the bearings on the chart are the same as those on the Earth. The word conformality means the same thing. The bearings or angles are correctly represented. The two words can be used interchangeably. There are two conditions which have to be satisfied if a projection is to be orthomorphic. The first is that meridians and parallels must cut at right angles on the chart. Let's see what happens if they don't. Look at this graphic. It represents a situation on the Earth. We have a rectangular shape, and the northeast corner is 2 miles north and 3 miles east from some datum. The bearing on the Earth from Oscar to X-ray is 0.56 degrees. Now suppose that the projection does not show meridians and parallels at right angles. This happens. The shape has become a rhomboid, and the bearings have been distorted. If the 90 degrees of angle between a meridian and a parallel are not correctly represented, how can any other angle be? It is therefore a necessary condition of orthomorphism that meridians and parallels cut at right angles on the chart. This does not mean that you have to have a rectangular graticule. This graticule may look odd, but it is orthomorphic. Meridians and parallels do cut at right angles. The second condition is to do with scale expansion. This graphic shows a situation on the Earth. We have a square-shaped piece of land, and the northeast corner is 3 miles north and 3 miles east of some datum. This gives a bearing on the Earth from Oscar to Yankee of 0.45 degrees. Suppose that our projection now expands the north scale more than the east scale. Our square shape has now become rectangular, and the chart bearing is now 0.35 degrees instead of 0.45. This chart is clearly not orthomorphic. This gives us our second condition for orthomorphism. Scale at any point on the chart, ideally, should be equal in all directions. If this is not possible, then scale must change at an equal rate in all directions. So now let's summarize. There are many projections available to us. Some properties cannot be captured, except on a globe. Scale can never be constant and correct. We can modify charts mathematically to give nearly constant scale in small areas, but not over large areas. The shapes of large areas cannot be represented perfectly. However, it is possible to represent the shapes of small areas reasonably accurately. All the other properties can be obtained on charts, but not all on the same chart. Different projections capture different properties. However, the one essential property for aviation is that angles on the chart must correctly represent angles on the Earth. This is less common in projections than you might think. This property is called orthomorphism, or conformality. A projection will be orthomorphic if it meets two essential conditions. The first is that meridians and parallels must cut at right angles on the chart. And the second is that scale at any point on the chart must be equal in all directions, or must change at an equal rate in all directions.